OG quantum hacker himself, Vadim Makarov.
Thank you. Unfortunately, I don't see you guys, so that's a bit of pity, but I can surely talk to a black hole. Today I'm going to tell you about how to break quantum key distribution, what attacks are possible, and I will tell you about the certification, government certification system that is being built for this technology, how to protect from attacks and certify that the systems are indeed secure, if they have the right countermeasures. And as I understand, you had a bit of an introduction into QKD. I don't know what you were told, but let me summarize it in 2 slides. Quantum key distribution is now an industry. There is industrial scale deployment of this technology in many countries. China is one of them. I'll just showing you an example that China at present, okay, 1 year ago, it had about 12,000 kilometers of backbone QKD network installed, and hundreds of customers in cities along this network. This is all fiber optics. Other countries also have deployment on a smaller scale. Europe, Russia, Japan, India, I believe. So I'm not going to recap the previous talks, but this is really QKD is now in commercial use in many countries. And another method to do QKD is to increase the distances to global scales by using a quantum key distribution satellite. So you can do fiber optic networks within one continent, but if you want to cross really long distances, then you would launch a satellite into an Earth orbit, and this satellite works as a trusted node. During it will do separate sessions with different ground stations and then exchange the keys between any pair of stations on the globe. So this is another possible communication channel, and indeed China has already demonstrated several quantum key distribution satellites, and other countries are catching up. Canada is going to launch something soon. So, given that the status of this technology is going into widespread use, you need to know how strong it really is against all kinds of hacking attacks. And this is what my research group is about. We try to hack this. In theory, quantum key distribution is unbreakable. If you execute the perfect quantum key distribution protocol, its security is based on the laws of physics, and it makes no other assumptions. The problem is, there is no such thing as a perfect implementation. The machines, devices that implement this perfect protocol are imperfect. They are made by people who make mistakes, or they have limited knowledge. The devices are complex. They typically contain about 20 different optical components that have all kinds of funny characteristics you can try to exploit. There is a big, rather large software code to make the devices operate. There are calibration routines that the perfect protocol does not concern about them, but to make the devices work, you need to calibrate, you need to align them, track timing, and so on. So there are complexities. And you can find many differences between the implementation and the perfect protocol. And very often when you have this difference, you can construct an efficient attack on the QKD protocol. Now, we know about 25 different kinds of attack you can do on QKD. And each attack uses different imperfections of the devices. Today, you will see some examples of attacks. So let's begin. Let's continue. And by the way, first I need to give you a setting in which the security of quantum key distribution is provided. In quantum key distribution, we have 2 devices, Alice, the sender, and Bob, the receiver. So Alice prepares quantum states of photons. She sends them over an optical communication channel towards Bob. Also, Alice and Bob have a classical communication channel like internet, and they do the protocol by exchanging some classical messages on this channel. to complement the optical channel. In the security setting, the eavesdropper Eve can do anything that the physics allows to both channels. She can do whatever. Eve is powerful. She can have a general quantum computer, she can have lossless channels, perfect quantum memory, arbitrary perfect quantum measurements, and anything that the physics allows, she can do to this optical channel. Also, she can listen to this classical channel, but unfortunately for Eve, she cannot replace messages in this classical channel because the protocol includes unconditional authentication to the messages. The classical part of the protocol is not encrypted, but it is strongly authenticated. So all Eve can do is to listen to this classical exchange. But she can listen and use this information as well to her advantage. One more thing we assume that everything about the devices themselves and their software is also known to Eve. So she knows everything, how the devices are constructed. This is time-honored Kerhov's principle that basically says the enemy knows how your cryptographic system is designed. She knows everything. The optical scheme, the software, she even knows the exact characteristics and exact imperfections that you have in your optical devices. And this might seem like a little bit too much power to give to the eavesdropper, but experience shows that this is a good assumption that needs to be done if you want your cryptographic system to hold the attacks. The only restriction we have on Eve is that she doesn't have a physical access into Alice's and Bob's boxes. So inside the boxes is physically secure from Eve's interaction. So she cannot put her hand inside and change something. But she knows everything that is going on. And in this setting with all-powerful Eve, we have to use our today's imperfect rudimentary quantum technology to provide security in this setting. How do we do about it? I will show you one example of attack. So Canada is about to launch a Canadian quantum key distribution satellite. This quantum key distribution satellite uses a receiver for single photons on the satellite. So this is a prototype of a polarization analyzer from this photon receiver in the satellite. Inside this box, there are beam splitters that separate, if you put input light from the ground station that reaches the satellite to this optical window, it will get separated into 4 different polarizations, as the protocol requires. Let's see what's inside this device. In our lab, we analyzed a prototype of this device that has the same optical scheme as this integrated construction, but it's a little bit easier to work with. You can see what's going on and you can align it. Inside this polarization analyzer, the input light from the ground station. So in the Canadian quantum satellite, the center is on the ground, and this is has to be a really long link, hundreds of kilometers to the satellite. And on Bob, we have a photon receiver. The input light from the input telescope gets focused and recollimated to a collimated beam that is about 1 millimeter in diameter. The beam goes through a non-polarizing beam splitter. This is a half-silvered mirror that randomly splits incoming photons with about 50% probability in one direction or the other. In one, regardless of their polarization, in one arm of this non-polarizing beam splitter, there is a polarizing beam splitter. This is a device, optical device, that splits vertical photons are reflected at 90 degrees, and horizontally polarized photons go through straight. In each output arm, there is a lens that focuses the photons into a core of a multimode fiber. The fiber then connects to a single photon detector that is not shown on this diagram. By the way, do you see my mouse on the screen?
Yes, we do. Yes, we do.
Good.
Yes,
Great.
we see your mouse on the screen.
Great. All right. In the other arm, the other arm is rotated 45 degrees. So physically rotated 45 degrees. Then there is again polarizing beam splitter, but now it splits two diagonal polarizations, left and right diagonal polarization from the input. And again, each polarization goes into its own multi-watt fiber to its own single photon detector. In the normal operation, when the satellite is successfully tracking the ground station, the input light beam from the ground, the photons, are aligned along the center of the optics such that they reach all four single photon detectors. So each last collimating lens is focusing light into the core of the multimode fiber within the core size, and each of the detectors has a chance to detect the polarization of the photon coming from the ground. So we asked a question: how can Eve hack this device without having a physical access to it? So she cannot change anything here, but she can do anything she likes with this free space beam. And we started messing with the free space beam. So we designed an eavesdropper that looks very similar to real Alice, but she deflects the beam to an angle, make the beam tilted. So when this is done, the beam tilts, and in effect, through all this optics, the focusing point at the end of the multimode fiber shifts laterally. And eventually, when you reach a critical angle, the point shifts outside the core of the fiber. It hits the cladding, and the light gets lost at this point. The photon doesn't reach the single photon detector. So there is a maximum angle at which this happens. And the four optical arms in this receiver cannot be perfectly identical. In the factory, the alignment is done to make them as close as possible to make the angles overlap. But Eve can always find an input angle when the light gets lost at this point for this polarization, gets lost at this point, gets lost for this point. But in just one channel, it is still focused within the core of the fiber, because there is no such thing as a perfect optical alignment. There will always be small differences between the arms. And only a detector of this polarization can see a photon. What Eve can do? Eve can deflect the photons in the communication channel. She is allowed to do this. This is not a quantum measurement. The angle is not used for information encoding. Eve does not try to measure polarization of the photons, so she will not introduce any errors in the transmission. She simply uses a prism or a mirror to deflect the input light a little bit. And she deflects it at exactly this angle that she knows only one detector can see photons at this angle. Bob receives a photon, and Bob reports publicly on the classical channel and says, I have had a photon detection. I successfully received this bit. But Eve knows that at this deflection angle, only one single photon detector could possibly detect a photon. The other three detectors didn't see them. So she knows the polarization Bob received, and she knows the actual bit value. So this is a direct leakage of the secret key. And by the way, this is called an efficiency mismatch attack. By varying the angle, Eve introduces a detection efficiency mismatch. One of the detectors remains sensitive, but the sensitivity of the other detectors is suppressed. She can find such angles for each of the four detectors, and if she uses those four angles, switches between them randomly, she knows for every click that Bob receives which detector in Bob has clicked. So this is indeed an efficient attack, and you could ask an engineer, this is a security problem. How do we close the security loophole? An optical engineer scratches his head and says, okay, we need to do something, and we need to make this range of input angles that is currently restricted by the core of each of the four fibers perfectly overlap. How do we do it? Why don't we put an aperture, a small aperture at the focal point of the first telescope? So indeed, we install a pinhole there, a pinhole of sufficiently small size that it restricts the range of input angles to an even narrower range. So, for example, the core of the fiber restricts to the input angles to something like 100 microradian cone, but this pinhole restricts it to an even narrower angle, for example, 50 microradian. And because this restriction is done before the photons are separated into 4 different polarizations, there will be no efficiency mismatch. The restriction will be exactly identical no matter what polarization is coming from the channel. So this appears to solve the problem. We took this Canadian, so this Canadian prototype indeed had this countermeasure installed because this is a known problem. So we put it under a test. We built this setup and we scanned the range of input angles. So here you can see the sensitivity of each of the 4 channels, H, V, diagonal and diagonal polarizations, plotted depending on the deflection angle of the input beam coming from the transmission line, transmission channel. So we scan something like 100 points here, 100 points here. So this is a scan containing 10,000 points. And the white and light color corresponds to normal detection efficiency, about 50% sensitivity, what you get from a normally functioning single photon detector. And the dark blue color is several orders of magnitude less, so about 4 orders of magnitude less sensitivity in that channel. So there is a big dynamic range here. And indeed, in normal alignment at 0,0 deflection angle, all 4 channels are sensitive to light. But if you deflect the input light to a certain angle, for example, to this angle where I'm pointing the mouse, channel H can still see the photons. But channel V has much less sensitivity, about 100 times less. And channel D also doesn't see the photons very well. And channel A also doesn't see the photons at this angle. So when Eve deflects the photons to this range of angles, only one channel is sensitive. You can find such angles to address each of the remaining 4 detectors as well. So the system, the unprotected receiver, can be efficiently attacked. This is the same diagram, but we scanned it after we installed the loophole. And the loophole makes the sensitivity range narrower. This is one effect. But more importantly, it makes the sensitivity to be exactly identical between the 4 channels. So even this diffraction pattern looks identical. Here we could find no attack angles, and the system seems to be secure. So is the problem solved? We need to design a counterattack because we are good hackers. We want to break this countermeasure. Does the audience have any ideas how we can circumvent this countermeasure?
Any ideas? No ideas here yet, Vadim.
Anything?
There's some discussions.
I'll give you 30 seconds.
Anything, Ben? There's a suggestion to change the focal point.
Change the focal point. Okay, yes. All right. To hit an edge of this pinhole. Okay, we tried this, but this is some kind of, this is a simpler idea and more beautiful idea. Any other suggestions?
Anything else? No, nothing else quite here.
As a school in Switzerland had a suggestion, students suggested that we equip the satellite with a high power laser that shoots back at Eve and destroy Eve. Yes, but this becomes an arms race, of course. All right, so you know what laser machining is. If you take a laser powerful enough, you can destroy things. You can physically melt material. And we as hackers don't like the presence of this countermeasure. So why don't we try to remotely destroy this countermeasure? We don't have a physical access to the receiver. This is prohibited. It's a secure device. But we can put any power we like into the communication channel. So we purchased a 20-watt laser diode. It's not expensive, by the way. It costs less than $1,000. Took this high-power laser diode and inserted it temporarily in the communication channel. And we illuminated this pinhole, the material of the pinhole, with a spot of light such a high power that we physically melted the material of the pinhole. So we did a little laser machining right inside Bob's device to remove the countermeasure. And after this, we could do the original attack. But we also lowered a little camera on the periscope to film sideways what happens to the pinhole inside Bob's device as we execute this attack. Here I have a video. This is the original pinhole. It's made of stainless steel with a little 20 micrometer diameter hole in this steel. So black is the actual opaque material. It's stainless steel, blackened. And here's the little hole that originally was filtering our input angles. Now I am switching on 3.5 watt laser for 20 seconds. The laser hits the material. It actually melts a much bigger hole in the pinhole. And after we switch off the laser, the entire countermeasure has been destroyed. Now we have 150 micrometer diameter hole, and it no longer functions as the countermeasure. We can then do the original efficiency mismatch attack. I don't hear. Can you repeat? Can you repeat the question? I don't hear you guys. All right. So the engineers have to be back to the drawing board and decide a counter measure against this counter attack. So this is how it works. It's an arms race. And of course, if you know what the attack is, you can think about possible ways to stop this attack, but you need to know what the attack is. So we had to do it in the lab to demonstrate that it indeed is possible. And nothing else got damaged in the setup. So we only machined the pinhole inside the setup. This is called the laser damage attack. Oh, sorry. So this study was financed several years ago by the Canadian Space Agency when I had a lab in Canada, and the Office of Naval Research. So the American taxpayer money was used to fund the study in Canada. Thank you very much, guys. Does anybody have questions at this point? There's no sound. I don't hear anything.
We just lost communication. You're back now.
Have you missed the presentation?
No, we just missed like the last minute or two.
Did you see the video of the pinhole exploding?
We saw the video of it melting, yes. But we can play it again. It looked really cool.
All right. So this is how we destroyed this countermeasure. Nothing else got damaged in the setup. And now the designers of the satellite have to design a countermeasure against this new attack. This study was funded by the Office of Naval Research and Canadian Space Agency about 8 years ago when I was in Canada. We destroyed a part of a quantum satellite, for sure. Now, if you have questions, this is a good time to ask. And if you don't, I can go on to the current studies that design certification for fiber optic commercial quantum key distribution systems. After Canada, I moved to Moscow. And the last several years, I worked with a Russian company, Curate. It's one of the companies that makes commercial QKD systems for fiber optic networks. And with this company, we both prepared this system for certification, and we looked what should be the requirements on the certification lab to protect the system against all known attacks all known vulnerabilities in its implementation. How to test that all the countermeasures are good. And this system, I don't know if the introductory talk has introduced you fiber optic QKD, but as I assume you know what the system is, I'll explain it in a moment. But what you need to know about the Russian certification. In Russia, the certification standards themselves are actually classified. And because I don't want the security clearance, I don't see the actual standards, and I cannot be a part of the team that actually does the certification. But what my lab can do, we developed all the methodology that can be used for this certification. So the development of the QKD systems in Russia itself, and the researchers who are developing methodology, they're looking for possible loopholes in this system. This is all open information. So you can buy the system, you can also get the engineering documentation for the system, all the blueprints, the software code under NDA, but this is not a secret information. We can design countermeasures, we can analyze the system for vulnerabilities and publish the report openly, and we can design test methodology in a lab. And after all this is complete, we transfer the test methodology to a different team that has security clearance. And those guys will do the actual government certification in Russia. But I don't know what is going on this side. I was on this team. We analyzed the system and we made a laundry list of all possible vulnerabilities in the system. Let's see how the system is made first. It has a sender Alice and receiver Bob. The system runs a polarization-based decoy state BB84 QKD protocol. So it has a pulse laser, pulsed at 312 megahertz with short pulses. The pulses pass an intensity modulator that randomly assigns one of the three different energies to each pulse. This is so-called decoy state protocol. They pass a polarization modulator that changes the polarization of each laser pulse to one of the four polarizations: vertical, horizontal, two diagonal polarizations. Then the pulses are attenuated with attenuators to a sufficient level such that at the output of Alice, they are at a mean intensity less than 1 photon per pulse. So it is a single photon signal at this point. Also, there is a synchronization channel at a different wavelength that synchronizes Alice and Bob. It's a separate channel, wavelength multiplexed into the same optical fiber. On the receiver side, the signal pulses, polarized photons, pass another polarization modulator that chooses the detection basis, one of the two detection bases. So either you are going to analyze in vertical horizontal basis, or if you apply 45 degrees rotation on this polarization modulator, then you are going to analyze plus minus 45 degrees polarization. And one polarizing beam splitter. In the previous scheme, in the satellite scheme, there was a beam splitter and 4 detectors. But in this scheme, we actively randomly choose the detection basis, and we only use one polarizing beam splitter and 2 detectors, 2 single photon detectors. Let's see what possible vulnerabilities we found in the system. The first important possible vulnerability is what protocol the system runs. And this system runs the BB84 decoy state protocol. This is the most studied quantum key distribution protocol in the community. There are general security proofs available for it. So we don't think the choice of protocol, it's a very important choice, but for this system, it's not a security problem because we use the most studied QKD protocol, and there are lots of papers with general security proofs to prove that this protocol is secure. This is not the case with some other commercial products, but it is the case with the product of this company. So this is not a problem. The next vulnerability. The system uses avalanche photodiodes in single photon detectors. And the single photon detectors have a few vulnerabilities. Basically, they can be blinded with sufficiently strong light. So if shines a bright light, a few milliwatts to those photodetectors, they get blind. And by modulating this input light, if can deterministically control the clicks of the single photon detectors, essentially force one of the detectors click at your choice. And this is a security problem. It's a very efficient attack. And indeed, we tested the single photon detectors made by this company. Of course, we found that they are susceptible to this attack. And the company has implemented a countermeasure, a photocurrent monitoring in the detectors that try to detect if the detectors are getting blinded and generally receive much more light than single photons. The countermeasure is partially efficient. It's not efficient. It doesn't have enough bandwidth. You can actually blind them temporarily in the pulsed mode. And now the company is making a better high-frequency version of this countermeasure, and we are going to test it soon. Also, we characterized a few other detector vulnerabilities. So this work is getting published. This is a high-risk vulnerability, by the way, because this attack is implementable today. If you want it, if the detectors don't have a countermeasure, then you can basically buy off-the-shelf equipment and eavesdrop on the channel with today's technology. Next, related problem. The detectors are gated. They are only sensitive to single photons within a short time window. And this time window is applied separately to each of the two detectors. And because there is no perfect alignment between the channels, just like what I have shown in the satellite demonstration, the time window is not perfectly aligned. So there can be timing at the edge of this time window when only one of the detectors is sensitive, or one of the detectors is more sensitive than the other. And it can control it by changing timing of the input signals. It's a very similar problem to what you have seen. And indeed, this is also a dangerous attack. You can execute it today. The company decided to make a countermeasure. In the countermeasure, they randomly swap the assignment of the two detectors to bit 0 and bit 1. So they apply at the phase modulator, in addition to the basis choice, they apply or not apply a pi, an additional pi phase shift that rotates the polarizations 90 degrees. And because the assignment of the detectors to bit 0 and 1 is randomly flipped, and if doesn't know the assignment, this essentially equalizes their timing characteristics. And this should remove this attack completely if the countermeasure is correctly working. So the design of the countermeasure eliminates this attack. Next possible problem. The single photon detectors, again, once one of the detectors has clicked, the detector goes blind for a certain time, called dead time. So it takes time to recover the sensitivity. And if one of the detectors has clicked and the other is still sensitive to photons, during the dead time, there is infinite efficiency mismatch. Again. So what has to be done? Both detectors have to be entered that time. So there is an electrical crosslink between the detectors. And also we found that we need to supplement this electrical crosslink with some post-processing to remove clicks when one of the detectors was in the dead time. So we only accept clicks into the row key when both detectors are sensitive to single photons. This is essentially done as post-processing. Again, this is a dangerous attack, but it has a well-defined countermeasure that is being implemented. Another problem. Now we move to the source, and in the source we have two electro-optical modulators, an intensity modulator and phase modulator. They prepare quantum states, and this information is secret. So the attacker should not know what intensity is prepared and should not know what polarization is prepared. An attacker can try to interrogate the modulators by injecting a bright pulse of light towards the source. So this bright pulse of light goes through all the attenuators. It passes the modulators, gets modulated by polarization and intensity, and some small fraction of this light is always going to be back reflected, because all optical components, all connectors, all devices always have a non-zero amount of back reflection. So some photons from this bright interrogating pulse are going to get back out in the communication channel. And there, the attacker can separate those photons and learn about the settings of the modulator by externally interrogating it. This is called a Trojan horse attack. And there is a theory proof that says if the bright input light pulse is sufficiently high energy, then enough photons will get back to externally read the intensity modulators and phase modulators. To protect against this attack, the system should have enough optical attenuation and additional optical isolators, optical diodes. So those are devices that pass light only in one direction. And all this attenuation should stack up to a sufficiently high attenuation such that no significant number of photons leak back, even when the attacker applies a very bright, very high energy light pulse. The attacker is essentially limited by the diameter of the fiber core. And we think that several tens of watts is the absolute maximum that the fiber can carry. If more light enters the fiber, the electrical field in the light is going to ionize the material and the fiber is going to explode. So there is a physical limit how bright the input pulse can be. And we have to provide enough isolation such that with this maximum limited power, physically limited power, sufficiently few photons leak, so this leakage is limited. How to guarantee that this isolation happens? We need to characterize each component for its transmission in both directions and sum up the transmission coefficients. And we have to do this characterization not only at 1550 nanometers, but we have to characterize them in a very wide spectral range. The fiber transmits light from anywhere to ultraviolet to beyond 2 microns. So it's transparent in visible range and a good portion of the infrared range. If it's not limited to 1500 nanometers, she can use a different wavelength for this attack. So all this characterization has to be done in a very wide range of wavelengths. This is a metrology task that we have solved in the metrology lab. Another attack, a similar attack, if can inject light such that enough light reaches the laser source. So it seeds the laser cavity with external photons. And this laser seeding can change the timing characteristics, it can increase the energy of the emitted pulse, and it can also lock the laser to a different wavelength from its normal operating wavelength. So this laser seeding is bad, and again, we have to attenuate this light to a level that doesn't cause the laser to lock to its emission. Again, characterize the transmission. Another attack. Again, light ejection attack. In this particular scheme, there is a power meter that sets the working point of the intensity modulator. And if Eve can get enough light to this internal classical power meter, she can also tamper with the operation, with the working point. Again, we need to characterize the overall attenuation in one direction. Another light injection attack on the source. Again, this is an attack on modulators. And it turns out modulators made of lithium niobate, an electro-optical material, can be illuminated with short wavelength light, blue and green light in a visible light. And this visible light ionizes the material of the phase modulators and creates a space charge inside the modulators. And this space charge changes the operating characteristics that actually attack security. And again, to protect against this induced photorefraction attack, we need to characterize the attenuation of all this transmission between the channel and the modulators in a very wide wavelength range. especially in the visible wavelength range where this attack is efficient. And we also need to test the modulators to determine when they start becoming sensitive, at what intensity this attack begins to work, to guarantee that this intensity doesn't reach there. A laser damage attack. Oh, you have seen a laser damage attack, and we did a laser damage on Bob. But on this system, we can do the laser damage attack on the center, on the source. And on this system, one primary target of the laser damage attack will be the optical attenuator. If we can melt this optical attenuator to decrease its attenuation, then we can compromise the security. Then the system will emit multi-photon signal instead of single photon signal. And we have tested different attenuators, and we know that the attenuators are generally vulnerable to this attack. They tend to break at a high enough power, and they reduce their attenuation very often. So we need to put a protective component, essentially a power limiter at the front of the system, the component that protects the rest of the system from the laser damage. And we have a good candidate for this component. We tested some optical isolators, and certain types of them actually work very well as a power limiter. They either break as a fuse, breaking the communication line, or they restrict the power transmitted to a safe level that doesn't damage the other components. So there is an extra protection needed against laser damage here. Another vulnerability, another detector vulnerability. Avalanche photodiodes actually emit a faint flash of light whenever they detect a photon because of the physics. There are many electrons crossing the photodiode, and some of them actually convert to photons, and there is a flash of light going back into the communication channel. And this flash of light can tell the eavesdropper which of the two detectors have clicked. So she will know the bit value by just looking at photons that get emitted back from Bob. And here we need to test, we need to characterize what is the photon emission probability. And it's a measurable number. And then this emission is broadband, spectrally broadband. The primary countermeasure is to put a spectral filter and limit sufficiently narrow band spectral filter such that the emission probability is sufficiently low and doesn't result in a big leakage of the key. So we need to spectrally characterize components here again. Another problem of the source, again, the source and the modulators, they have many imperfections. And one of the imperfections, the modulators are working at 312 megahertz and prepare states at quite a high repetition rate. And the security proof, the protocol requires that the choice of the state is independent between the bits. But actually, because the modulators have a memory effect and the electronics bandwidth is limited, the currently emitted state is a little bit affected by the previously emitted states. So there is an intra-symbol interference between the bits here. And this actually compromises the security again. So we need to measure what the problem is. So we measure the sequence of states, and we measure exactly how big the intra-symbol interference is, and we try to account it in security proof. Source characterization has to be done. Another problem, imperfect state preparation, and this is a static, it's not intra-symbol interference, it's not dynamic, but the modulators don't prepare exactly what we ask them. There is no such thing as 90 degrees polarization. It's always going to be a bit less or a bit more, 89.5, 91.3, and such static deviations from the prescribed values also reduce the secure key rate. We need to accurately measure the polarization and intensities and account those static imperfections in the security proof. They reduce the key rate. Another problem. Oh, I love this problem. This is the most expensive security problem that occurred to this manufacturer. It turns out that they do several calibration routines for this system. By employing photons going through the communication channel. So essentially, they have a service routine when they switch on the source and look at the photon detections, But this routine, it doesn't do key generation. It's just to set several internal parameters, such as the working point of the intensity modulator, the bias on the intensity modulator, the work point, the bias on the phase modulator, the bias on this phase modulator. And they also adjust the timing of the gates and the detectors during this routine. And if nobody tampers with this routine, this is secure. But the problem is, Eve can always change the timing and other characteristics of the photons going through the channel during this calibration routine. And essentially, she can set any of those parameters to a value she wants. A horrible problem. And the manufacturer had to work a lot to eliminate those calibration routines. They moved the calibration of those modulators inside Alice. So one of them is now only calibrated using the internal power meter, and the other calibration has been done at the factory, and it doesn't change after the system deployment. And for those three calibrations, the timing of the gates and the work point of this phase modulator, we think that the four-state countermeasure, the random flipping of the detector gates, they apply it in response to a different attack, also makes it safe to keep this calibration routine through the communication channel. So Eve can try to tamper with those three parameters, but we don't see any attack yet where this helps her. So it seems to be safe with this countermeasure applied. Another problem. This is not a problem, but this is an actual requirement of the protocol. The random bit and basis choices, the random intensity choices, and the random basis choices have to be generated by a physical quantum random number generator, a quantum random number generator. If you use a mathematical random number generator, that's not good. Mathematical generators are predictable, so you need a physical randomness source, preferably quantum. And we had to remind the manufacturer that they actually need to install such device into Alice and Bob. When we got the system, it lacked it. But they know, they agree, and they are adding it to the scheme. And the last problem, when the vendor assembles this QKD system, they buy most of the components from external suppliers. So everything, practically everything in the optical scheme comes from companies located in China, in Taiwan, in Canada, in the United States. Each component they get from an external manufacturer. And we see many ways in which an external manufacturer can tamper with the characteristics of the components surreptitiously, change a little bit, or install a modification in the component that makes it insecure to use this component. But this modification is done in such a way that during the assembly and manufacturing process, the QKD system doesn't notice that the component has been compromised. So the intentional compromise in the chain of supply for components is a big problem. And this problem is not unique to quantum cryptography. It exists in all the classical security devices. You either need to trust the manufacturers, or you need to examine the devices coming from an external party very well. And we just simply advise the manufacturer to ask the Russian National Security Agency what to do and how to mitigate this problem. In summary, we examined 15 different potential vulnerabilities in this commercial fiber optic QKD system. 4 of those vulnerabilities were high risk in the sense that the vulnerability was confirmed to exist, and an attack on it can be constructed with today's technology. So no future technology required, no quantum computer. You can simply buy components on the market and build an eavesdropping device for those 4 problems. For those 4 problems, the manufacturer has implemented countermeasures. And this has delayed the publication of this report. So this entire report is published, but it took more than a year for the manufacturer to design the countermeasures and deploy them. And we have recommended most of those vulnerabilities to a formal security certification by a certification lab. The question is what this lab should be. The lab, we are prototyping all the certification test benches. This is a wideband characterization test bench, detector testing setup against detector vulnerabilities. This is the characterization of state preparation. This is detector backflash, so we use a high sensitivity single photon detector to measure the backflash. And this is the laser damage test bench. This is a 6-watt laser. And we use it to subject the component. We damage the component using this high-power fiber amplifier. All right. And I have to mention that last year, a year ago, the International Standards Organization, ISO, has published a certification standards for all the known vulnerabilities in quantum key distribution. This is an excerpt of the table of content. You see that there are about 10 tests on the source that have to be done, about 10 tests on the receiver device that have to be done. And if you open one of the chapters, you can see that the test actually prescribes what the test setup should be and the general procedure for the test. So the certification standards, actually one standard, international standard, has just been published. And now we are awaiting the certified accredited labs to appear. So the quantum key distribution is very soon getting formal certification according to international standards. This is really coming. This in Russia, this is coming this year. In Europe, there is a program that aims to have the labs operational in 3-4 years from now, and other countries are also making an effort to make national certification. Thank you for attention. Any questions?
Thank you very much, Vadim. Any questions? Come forth, ask. Any questions, Ben? No questions at this exact moment, Vadim. How can they get a hold of you?
How many people are listening? Roughly 100? Less?
More like sort of 40, 50 at the moment. 20,
40,
40.
Very nice to see you guys. I don't see you, but I remember such events. I was in the Netherlands in the last Dutch event. Very glad to speak to you and see you in person next August in the Netherlands. I will be there.
We should get you over to DEF CON as well.
Yes, and if you Google my name, you will very quickly see my email address. Oh yes, at DEF CON. No, it's in the United States. It's a pain in the ass to get a visa. I'm sorry.
Okay, fair enough. But if you'll be in the Netherlands in August.
Yes, in Netherlands in August.
Perfect. If there's no questions right now,
you can email me.
Thank you so much for your time, Vadim. Yeah.
Sure, there's my email address. This is the laboratory website. Go there, you find my email, you can ask questions.
Amazing. Thank you very much, Vadim.
See you guys.